band or different band, we are able to create service. And these services were not limited on the physical infrastructure, frequency bands, and the radio spectrum. So that's where the new number one principle for the 5G air interface design, which is the slicing between the applications, which are very different for the massive connectivity, the sensor data, and the important for the command to control the car driving. So they are not the same. Therefore, there will be a programmability in the air interface to serve them well. Second one is the spectral efficiency. I still believe there's a lot of room to make a spectrum efficiency and yet another 3 times or more. So these are the combination of the technology that we need optimize them together as a joint air interface. I listed, for example, a few things that we need to do in 5G, new radio access, multiple access scheme, the sparse sequence code, multiple access, or filter OFDM, which can utilize all the spectrum aspect and also further optimize the usage scenario. The coding, better coding, the shorter so-called transmission time interval, the frame structure, and also the signaling reduction. These are all contribute together. It could be getting to 3 times or also new spectrum efficiency. That's going to be a huge value for the future generation of the 5G in terms of even serving the eMBB service. So for the other 2 service, for sure there will be a shorter latency, maybe 10 times more, more reduction or less latency compared to today we have, and also the number of the links will be 100 times more. So all this technology proposal need validated in the field so that we can make a standards or a product or make a market. We launched the activity, a relatively large-scale activity to do this type of a technology. I will give you a few flavors. 2013, we did a lab test of the interface candidate technology of several. For example, the sparse sequence multiple access. We did full duplex test and measurement and the design. So today, it will be around, very well with the MIMO scheme around about 1 watts transmission and with pretty decent about 120 dB cancellation. And the other is a 50 gigabits base station, which is utilize the current cellular bands that we designed in the 2012 and 2013. And then also the all virtualized radio running the radio interface in the conventional CPU or off-the-shelf processor. And the other is the millimeter wave beam tracking mechanisms and the technology that we don't understand well before. So this is the thing that for the utilize the higher spectrum millimeter wave. In 2014, we did a single user testing or field trial. These are still the benchmark, I think the record in the industry even today, with 32 by 32 transmission chain, 200 megahertz between the bands utilized between the 1.7 to 2.7 bands. There are few bands aggregate together about 200 meg. We are able to reach 10 gig also, the single user speed. This is the potential for the sub 6 gigahertz spectrum that we utilize. And then about 60 gigahertz, 6 gigahertz, we did an E-band transmission, which is about 9 gigahertz aggregate together with a 2x2 MIMO 64 QAM. We reach even 115 gigabits per second. This is still the record speed for for this type of a transmission. And as I mentioned before, the allocation, the potential allocation for the millimeter wave in that range, for this Congress, even we get additional 6 gigahertz. So potentially the access we were talking about is about maybe 2 or 3 gigahertz bandwidth, and with some MIMO or beamforming technology, that's probably the state of art of the speed. So this is the thing we did in 2013 and 2014. And in 2014, we also did some other tests. So lower 6 gigahertz outdoor testing of the transmission of, for example, this sparse-coded multiple access. Many times or 3 times more precisely links we can validate it in the field compared to OFDM. And we did also, in 2014, early time, we did an indoor test of line of sight fixed beam millimeter wave transmission with more than 100 gigabits per second. We did also outdoor early year 2014 March outdoor field trial with the beam tracking, and with about, at that time, about 40 also minutes, millisecond beam alignment time, and with a 2.2 gigabits per second with these links in the outdoor. So these are the link level in the more outdoor environment for sub 6 gigahertz and above 6 gigahertz. And this year, there's a large scale trial jointly with NTT Docomo. This is we are able to achieve the following benchmark of the speed. So this is the test in the band 40. So if you know band 40, that's the 3GPP bands of the 2.3 gigahertz consecutive TDD version of 100 megabits consecutive. Then the design is 64 radio transmission, the transceiver in the base station side, and then we have more than 30 UEs as a multi-user to access. So the result turned out we have about 24 MIMO stream can be transmitted concurrently. So this is the one that probably it is the largest link for the EMBB connection we have. And the peak rate we measured is about 3.6 gigabits per second in the 100 megahertz bandwidth in the real environment. And also spectral efficiency, there's algorithm improvement in terms of pre-coding algorithm. So it is about 50 BPS per hertz spectral efficiency. And this is already exceeding more than 3 times compared to LTE we can do today. So this is one large-scale trial in terms of an EMBB scenario. And within the same set of the trial, we also tested the technology I mentioned before in order to jointly design them to have a higher spectral efficiency. For example, for the sparse-coded multiple access scheme, we in the field, we measured about 3 times more connections compared to LTE we have today. So that's the non-orthogonal access dimension expansion. And then about 1.5 time of throughput in the downlink. For the filter OFDM, we can recover all the guard band we used to have, and also we can run asynchronized, uncoordinated slicing in the different subbands and without a performance penalty. And also the coding gain we managed to see in the field compared to the LTE turbo codes. There are a lot of, in the short packet, we have a almost 2 dB gain, and all the average is 0.5 dB. This translates about 10% spectral efficiency gain. and also the layers. What important is these sets of combination of technology allow us to do the slicing of the air interface. That means the programmability for different scenario and the different usage cases for the future use of the 5G. So these are the current tests that we, especially I pick a few with Docomo and also with some other people, which not in the public. So the progress is very encouraging. That means we do have potentially a technology solution to meet 5G requirement. And these are all even in the very classical radio aspect, there is a lot of room for improvement and for the 5G. So what about the network? This is something that I think we need some revolutionary thinking to redesign the entire network. So all the current progress today we have is, as we all know, this NFV and SDN, meaning that virtualize the network in the cloud technology. But that's not the changing of the network architecture. It is a mean of an implementation or more efficient or flexible implementation. And 5G also need a re-architecture or new architecture for the network. And slicing is the direction to go, but slicing is not a complete architecture solution. So the architecture solution here today is, we believe, is an application-driven network, meaning that we are not going to map all the application into a homogeneous pipe and then run the service over the pipe, manage the QoS. In this paradigm, that means the network will generate it specifically for that application, and it's end-to-end network, virtualized network, and automated generation network. And to build a network for an application, it is like an internet service style. When you have a service, you try, and if it is grow, it becomes a stable network. If it is not, make a commercial success, and automatically you don't active that piece of a slice. And this will make many potential interesting application innovation on top of 5G, and we don't need a business case for carrier and vendor to decide what type of service we will launch, and it will make money, right? So this is the essential merit for the ADN, that is the application-driven network. So on the nutshell, this network need a lot of restructuring and design, and also research work need to be done. Some theoretical basis is for these even three triangle I mentioned on the first page of the application, their traffic model, their network topology model are very different. We can compromise all these requirements, make a average network to serve this, or with this model we can really optimize different model with different design. So the key is that there's a need to introduce these three distinct layers in this architecture. So service plan, so you need an abstraction of the service, and then control plan, and this control plan is a two-layer. So there's an abstraction of the network control, and then the data plan. So the information flow level is abstract with a different slice. So these are the, we will see a lot of talking and discussion on this down the road about, and also interesting service will be running on top of this. This is the nutshell or the snapshot of the early 5G is a way less even than the tip of the iceberg of I mentioned what really 5G will be. Thank you.